This is Dr. Shankaraiah from Department of Physics. Today I am going to discuss nanotechnology, which is module 5 in applied physics. So in nanotechnology, the first topic is nanoscale. So today's presentation, I will discuss about nanoscale in this presentation. So what is nanoscale? The word nano is derived from a Greek word meaning dwarf. Nano means dwarf. So this is a Greek word. Okay. So are extremely small. So nano is derived from a Greek word, and the meaning of this nano is dwarf or extremely small. Means a billionth part of a unit. Billionth part of a unit. So 1 nanometer is 1 billionth part of a meter. Okay. So a nanometer or nanometer is 1000 millionth of a meter. That is 1 nanometer is 10 power minus 9 meters or 10 power minus 6 millimeters. 1 millimeter is how many meters? 10 power minus 3 meter. So that is why 1 nanometer, which is equal to 10 power minus 9 meters, we can write this as 10 power minus 6 into 10 power minus 3 meters. Okay, because 1 meter is 10 power minus 3 millimeters. So that is why we can write 10 power minus 6 millimeters, because 1 millimeter is 10 power minus 3 meters. So this 10 power 1 nanometer can also written as 10 power minus 6 millimeters. Okay, or 1 angstroms. 10 angstroms, no sorry, this is 10 angstroms, because 1 angstrom is how much? 1 angstrom is 10 power minus 10 meters. So 10 power minus 10, so here it is saying, so 10 power 10 minus meters, so here we have, so 10 power minus 9 meters, so that is why I am writing here as 10 angstroms. 1 nanometer is 10 angstroms, because 1 nanometer is 10 power minus 9 meters. So then it will become 10 into 10 power minus 10. So that is 10 power minus 9 meters. You can understand this as why it is 10 angstroms. It is 10 into 10 power minus 10 meters. 10 into 10 power minus 10 is how much? 10 power minus 9 meters. So 10 angstroms are 1 nanometer is 10 angstroms or 10 power minus 9 meters or 10 power minus 6 millimeters. 1 nanometer spans 3 to 5 atoms lined up in a narrow. So how do we understand nanometer in terms of atoms? If we are thinking about atoms in a material, so what does this nanometer means in a material? So you can think of 1 nanometer is around 3 to 5 atoms. If you think of all the atoms are lined up in a row, so 1 nanometer means around 3 to 5 atoms size. You can think of it as 1 nanometer. Okay. For comparison, a single human hair is around 80,000 nanometers. See, human hair is 80,000 nanometers wide. Okay. So that much is small is a nanometer. And a red blood cell is around 7,000 nanometers wide. Okay. So a nanometer is 10 power minus 9 meters or 10 angstroms or 10 power minus 6 millimeters. To think of it in terms of atoms in a material, you can think of in 1 nanometer space, there can be 3 to 5 atoms that can arranged in a row. Or you can physically you can think of a human hair as around 80,000 nanometers wide. Okay, so a nanometer is very extremely small. That is why it is mentioned as, it is derived from a Greek word dwarf or extremely small. Nano means dwarf or extremely small. It is 80,000 nanometers. A human human hair is around 80,000 nanometers. Okay, so nanometers very very small and extremely small. Okay. Scientists and engineers are nowadays interested in the nanoscale, right? Scientists and engineers are nowadays interested in the nanoscale, which may be taken as 100 nanometers to 0.2 nanometers. So nowadays, scientists and engineers, when we say that what is nanometer range or what is the scale, what you can define it as a nanoscale, you can take this 100 nanometers to 0.2 nanometers. 0.2 nanometers. So this is what nowadays scientists and engineers are using it as a nanoscale. When they are saying nanoscale, that means the length scale is around 100 nanometers to 0.2 nanometers. So in this range, we can define it as a nanoscale. Below this lies atomic scale, which is around 0.1 nanometers. So below 0.2 nanometers, we are going to atomic scale, which is around 0.1 nanometers. So therefore, the nano world is a borderland between the quantum world and macro world. Okay, so nano scale or nano world, nanoscale is around 100 nanometers to 0.2 nanometers. So we are neither in macro world nor in quantum world. It is a borderline between macro world and quantum world. So if you think of this as macro world, which is around centimeters, millimeters, and this is around quantum world, which is angstrom level, and now this range is a nanoscale or nano world. This is what is nano world. So nano world is a borderland between quantum world and macro world. So nanoscale, nowadays we are scientists and engineering using this range 100 nanometers to 0.2 nanometers as nanoscale. Below 0.2 nanometers you have atomic quantum world, and above 100 nanometers you have macro world, going to millimeters range, millimeters, centimeters. Okay. So nanoscale is a borderland between macro world and quantum world. Okay. So what is this nanotechnology and how is it useful? So nanotechnology is the day-to-day developing subject with large number of applications. So nanotechnology is developing every day, right? And based on development, if you develop a new instrument or new device which we can use to look at the atomic scale even deeper into the atomic scale, we can use those technology or devices in different applications, right? So it is a developing subject, and as it develops more and more, there will be more and more applications we will find. Nanotechnology has a potential to create many new materials and devices with wide-ranging applications. Okay, it has potential to create many new materials and devices. Nanotechnology, using nanotechnology, we can create many new devices and materials where we can use these materials and devices in many applications such as medicine, in electronics, energy production. For example, few. Okay. So as this nanotechnology is developing every day, day by day it is developing with lots of applications, and it has potential to create many new materials and new devices which we can use in medicine and electronics and many energy productions. And these are some of the few applications, but there are many applications which we will discuss in one of the presentation. Nanotechnology is the design and development of techniques. So if there is a question like what do you mean by nanotechnology, you have been saying nanotechnology, nanoscale and so forth, what is it? So what is this nanotechnology? Okay, so nanotechnology is design and development of techniques, instruments and devices for fabrication, characterization and applications of nanoparticles. So in nanotechnology is basically design and development of techniques, various techniques. How do we develop different instruments or devices for fabrication? Suppose if you want to fabricate a new material, so you need to have an instrument, right? you need to have a technique. So nanotechnology involves all these designs and development of techniques and various instruments. Though all these techniques and designs and instruments and devices can be used for fabrication of a new material or to characterize the new material. Suppose we have fabricated a new material using some nanotechnologies, such as a new instrument or new technique. Using such a new technique or instrument, we have fabricated a new material, and we need to understand what that material looks like. Is it a crystal? Is it a amorphous material? Okay, to understand the structure, we need to have some characterization techniques, characterization instruments, right? So we can use, so nanotechnology also involves characterization devices to characterize this material, new fabricated materials, and where can we use this such newly developed fabricated materials. Okay, so all these are defined as nanotechnology. Nanotechnology is design and development of techniques, instruments, and devices. All these, where do we use all these instrument designs and devices? To fabricate a new material, to characterize the such a fabricated new material, and to understand where this fabricated, studied new material can be used. Okay, so this is what is a nanotechnology, right? So many diagnostic instruments like transmission electron microscope (TEM). This transmission electron microscope can be used to look at the structure of a material. How does the domains or atoms are sitting in a new material? A scanning electron microscope. This also we can use to look at the structure of the material. And atomic force microscopy, magnetic resonance, MRI scanning, where we use this in medicine, have been used, invented in the nanotechnology. So using this nanotechnology, there are many instruments that are developed, such as transmission electron microscopy and scanning tunneling electron microscope and atomic force microscope. All these materials, all these devices are used to study, understand the structure of new materials, or structure of any atom. And MRI, magnetic resonance imaging, this instrument which is developed using nanotechnology is being used in medicine to look at, to scan different parts of our human body, for example, brain. So these are all very useful and have many applications in medicine and to understand our study of research or materials. Okay. So nanoscience is the basic of nanotechnology. The nanoscience relies more on quantum theory. Okay. So how do we understand this nanotechnology? Nanotechnology is design or development of new instrument, techniques, and devices. Okay, we are designing new device, for example, or new instrument, for example, to fabricate or to characterize a material, right? So how do we understand how we are able to find out all these structures, for example, of a material using transmission electron microscope? So to understand this nanotechnology, we use nanoscience. Okay, so nanoscience is the basic of nanotechnology. So this nanoscience relies more on quantum theory. So the nanoscience which is used to understand the nanotechnology, this nanoscience relies mostly on quantum theory. So nanoscience can be defined as the study of phenomenon. So what do we mean by nanoscience? We are saying that nanoscience is a basic of nanotechnology, and nanoscience is mostly relies on quantum theory. So what is this nanoscience? Nanoscience is a phenomenon defined as the study of phenomenon and manipulation of materials at atomic, molecular, and macromolecular scale, where properties differ significantly from those at large scales. This nanoscience is a study of phenomenon or manipulation of materials at different scales, atomic scale, molecular scale, and macromolecular scale, where we look at the properties. When we look at the properties of materials at macro scale and materials at micro scale or nano scale, there is a huge difference in the properties of these materials. So nanoscience is a study. We can use nanoscience to understand why the properties of material change when we go from centimeter scales to nanoscales. Okay, so that is what is nanoscience. So nanoscience will help us to understand why the properties of materials changing when we go from centimeter scale or the macro scale to micro scale, which is like angstrom scale. Okay, so how did this nanotechnology started, right? So we have defined what is nanoscale, and then nanotechnology. What do we mean by nanotechnology, and what is nanoscience, so on and so forth. Now we need to understand where did it come from, how did it start, how does this nanotechnology started, what is the beginnings of this nanotechnology. The word nanotechnology is relatively new. The existence of nanostructure is not new. We all know this the word nanotechnology is relatively new, but the nanostructures are not new, because nanostructures have been studied from decades earlier. Okay, so for example, in 4th century, Roman makers fabricated glasses containing nano-sized materials. So no, nanostructures have been studied. The study of these nanostructures are there even from 4th century. But the word nanotechnology has started relatively new. Okay, so in 4th century itself, the nanostructures, for example, these Roman glass makers, they have fabricated glasses containing nano-sized materials. Similarly, gold nanoparticles are made long ago. So these nanoparticles have been made, gold nanoparticles, for example, have been made long ago. Right? So the concept of nanotechnology was first given by Richard Feynman. So the first concept, okay, there is some technology called nanotechnology, which we can use to understand various properties of materials, various phenomenon that can occur in materials. That the concept is first given by Richard Feynman. Okay, so the first concept about nanotechnology is given by this famous scientist Richard Feynman. So in 18th century, British scientists Thomas Wedgwood and Sir Humphrey Davy were able to provide images using nitrate, chloride, but their images were not permanent. So in 18th century, there are various scientists, and they were able to provide images of this nitrate and chloride, but their images were not clear about this nanotechnology. In 1960, Richard Feynman presented a visionary and prophetic lecture at a meeting of American Physical Society entitled "There is Plenty of Room at the Bottom." Around 1960, Richard Feynman presented a lecture in American Physical Society meeting. The title of this meeting or presentation of Richard Feynman was "There is Plenty of Room at the Bottom," where he speculated on the possibility and potent of nano-sized materials. There is plenty of room at the bottom. That means as you go down in scale, from centimeter scale, millimeter scale, micro scale, and nano scale, as you go down in the length scale of this material, as you reduce the size of these materials, then there can be a plenty of room. There can be very new materials that can be fabricated, which can be used in various applications. So that is what he tried to explain in this presentation. So there is plenty of room at the bottom. So where he speculated on the possibility of potent of nano-sized material. So the first concept of nanotechnology is given by Richard Feynman, and in a American Physical Society, like he gave a lecture entitled as "There is Plenty of Room at the Bottom," imagining about this new nano-sized materials. The term nanotechnology was defined by Tokyo Science University professor Norio Taniguchi in 1974 paper as follows. So the first term nanotechnology was defined by this Tokyo University professor Norio Taniguchi in 1974 in his paper. Nanotechnology mainly consists of the processing, separation, consolidation, and deformation of materials by one atom or by one molecule. Okay. So he defined this term nanotechnology. First, the concept is given by Richard Feynman, but the term nanotechnology is defined by this scientist from Tokyo Science University, and he said in his paper that nanotechnology mainly consists of processing of separation, consolidation, and deformation of materials by one atom or by one molecule. So nanotechnology basically focus processing, separation, or deformation of materials by one atom or one molecule. So in this nanotechnology, you can look at individual atoms or individual molecules, and you can study them, or you can process them, you can separate them, you can do various, you can study various properties of this using nanotechnology at atomic level, one atom or one molecule. Nanomaterials means a material whose size is in nano range. Okay, so that is about origin of nanotechnology, who started this nanotechnology, and who defined this term nanotechnology, and who gave the concept of nanotechnology. And then coming to these nanomaterials. Nanomaterials means a material whose size in nano range. So we have defined what is this nanoscale, right? So when we are going to say a given material is a nanomaterial, when the material is having size in this nanoscale, then we can call that material as a nanomaterial. So this is an answer which may be generally thought, but there is an implicit meaning. Okay, so what do you mean by this nanoscale, and when we are going to call this as nanomaterial? Okay. Suppose consider a gold biscuit of 100 centimeter cube cut into two pieces. Okay, so we have taken a gold biscuit which is around 100 centimeter, 3-dimension, right? So there is a 3-dimensional gold biscuit is around 100 centimeters cube. So we have cut this into two parts, right? So when we cut this into two parts, so one is 50 and the other one is 50 centimeter, right? So 50 centimeter cube and 50 centimeter cube. Yeah. So no properties are changed except its size. Yeah. So whatever properties we have studied when we taken this 100 gold biscuit of 100 centimeter cube size, we studied for example, we have studied the properties of gold biscuit, various properties. Okay. So we have noted all the properties of this 100 centimeter cube gold biscuit. Fine. Now we have cut this gold biscuit which is 100 centimeter cube into two parts, equal parts. So each gold biscuit is now 50 centimeter cube. Okay. So when we cut this into two pieces and look at the properties, there will be no change in the properties of these two independent equal pieces of gold except its size. Earlier it was 100 centimeter cube. Now there are two such small cubes, each around 50 centimeter cube. Only size changed except no properties changed. So divide into further small pieces, then also there would not be any change in properties. Okay, now we have further divided. For example, divided into four parts, 25 cube and 25 cube, 25 cube and 25. There are four small biscuit cubes. When we look at the properties of these four biscuit cubes, we will find no properties changed except their size is reduced into now 1/4 of the original. Now, so thus the macroscopic solid pieces of the material possess size independent properties. Okay, so whether it is 100 centimeter cube or 25 centimeter cube or 10 centimeter cube, it doesn't, the properties of this material doesn't change. Okay, so the macroscopic solid pieces of the material possess size independent properties. So we are when we cut this 100 centimeter cube into 50 centimeter cube, 25 centimeter cube, and then 12.5 centimeter cube, all these are in centimeter range. Okay, so that is why we are calling this gold biscuit as macroscopic solid piece. Okay, so these macroscopic solid pieces of these materials do not change their properties. Okay, so that is why we are saying macroscopic solid pieces materials possess size independent properties. Okay, when you are in macro scale, when you are in centimeter scale, as you cut further and further until you are in centimeter cube, so you will be in macro scale and there will be no change in properties of these materials. So that is what we are saying. Okay, so it was found that when gold is divided into the fine grains of nearly 50 nanometers. Okay, so we have divided further as we keep on dividing this 100 centimeter cube biscuit into smaller and smaller and smaller up to nearly around 50 nanometer each. So along each side of this cube, we have 50 nanometers, 50 nanometer, 50 nanometer, 50 nanometer. Okay, around 50 nanometer, when we divided this gold biscuit into small pieces of having length around one of the axis is 50 nanometers, then the properties like density, color, hardness, melting point, resistivity, etc. are changed. Okay, so as you when you take the material which is in macro scale around centimeter scale, now we have divided further and further and we went down into nanometer around 50 nanometers, then we found that the properties of this material changing. So then we are saying that the microscopic pieces possess size dependent properties. As we went down into nanometer scale, then we find that there is a change in the properties of the material. So thus the size dependency is an essential property of a material. Okay, when a material is changing its properties, then we can call that material as a nanomaterial. So that is why we are defining it as size dependency is an essential property of nanomaterials. Yeah, so now we have defined what is nanomaterial by taking this example of a gold biscuit around 100 centimeter cube, and we have divided into smaller and small pieces and went down into 50 nanometer length scale and found that then only the properties change. Okay, so that is where we have defined that then that material which is around which is a gold biscuit which was divided further and further small grains around 50 nanometer, then that becomes as a nanomaterial. So a nanomaterial is defined as material having one of its dimensions in nano range. So as we divided this gold biscuit which was around 100 centimeter cube into half and quarters, we found out that when one of the dimension of this nanomaterial is in the nano range. So we found out that when we taken this 100 centimeter cube gold biscuit and divided into 50 centimeter cube and so on and so forth, when we have gone down into 50 nanometers, only then we found out that various properties are changing. This gold material's properties are changing. Okay, so then nanomaterial is defined as a material having one of its dimension in nano range. That means one of the length scale is in nano range. So this gold biscuit which was originally around 100 centimeter cube now cut down into 50 nanometers. So that is why we are in nano range, and hence we can define this gold biscuit which is around 50 nanometer as a nanomaterial. Nanomaterials could be defined as those materials which have structured components with size less than 100 nanometer at least in one dimension. Here we have taken 100 centimeter cube. So it is a cube which is having around 100 centimeters along x, y, z directions. This gold biscuit is having length around 100 centimeters around each of these three dimensions. Now, when we have cut down into smaller and smaller pieces, we have gone into 50 nanometers. So, the 50 nanometers can be around x-axis, y-axis or z-axis. So, any one of the axis must be in nanoscale. Only then we can define that material as nanomaterial. Okay. So, that is exactly the meaning of nanomaterial. How can we, when can we say a material is a nanomaterial? Okay. So generally, if one dimension, if the material, if the nanoscale is in one dimension, then it is called quantum well. Our example is thin film. We have said that when we are taking macro scale material and divided or cut into smaller and smaller pieces, then when we are going to say that material as a nanomaterial, when the dimension one of the dimension along x or y or z along one of the dimension the length scale must be in nanoscale, then we can say that material as a nanomaterial. For example, if in one dimension there is a nano scale, then that is called as quantum well, and it is thin film is the example of such a quantum well or material nanomaterial. If the nanoscale is in two dimension, nano range is in two dimension, it is called quantum wire, or carbon nanotube is an example of nanomaterial where the length nanoscale is along x and y axis. Suppose the nano range is around 3 dimensions. Along x-axis nanoscale is there, along y-axis nanoscale is there, along z-axis also nanoscale is there. What do you mean by the length scale is around 100 nanometers to 0.2 nanometers along x-axis, along y-axis, and z-axis. So when along all 3 dimensions there is a nanoscale, then that material is called a quantum dot, and example of such a quantum dot is a colloid. Okay, so this is how we define quantum nano materials in 1 dimension and 2 dimensions and 3 dimensions. So these are some of the reference books which I've used in this presentation. And to summarize, today I've discussed about nanoscale. I've discussed about nanoscale. Starting with, I've discussed about nanoscale, and then I've discussed about nanotechnology. What is nanotechnology? Then I have defined about origin of nanotechnology. So where did this nanotechnology came from, or who defined this term nanotechnology first? Then I have also discussed about nanomaterials. Also discussed about nanomaterials in 1 dimension, 2 dimensions, and 3 dimensions. So in the next presentation, I will discuss about the next topics. For example, maybe applications of these nanomaterials in science and technology. Okay, so I'm going to end here. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.